Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand humans? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. It is now time to welcome into the studio and your opportunity to talk to the man himself. Ask him any question. If he knows, he knows. If he doesn't, he doesn't. The very delightful Dr. Dave is here live in the studio.
Good evening, Sue.
Happy New Year to you.
Happy New Year to you and everybody else who's out there.
Absolutely. Have you got any science stories for us?
I saw quite an interesting little story this week. It's about a cute little creature called a Pacific spookfish. It's got very unusual eyes. Now, almost all creatures which we've found so far, they've got eyes which work roughly like ours. They've got a lens at the front, which focuses light onto the back of our eye, onto the retina. So you get an upside-down image of what's outside on the back of the retina. You've got lots of little light-sensitive cells, and it detects where the lights come from by where it is in the picture, and you build a picture of the world outside, and you can see stuff. Now, all eyes that we know of either use a lens or just a little hole. Some of them have a little pinhole, so you've got basically a pinhole camera. But none of them that people have found up till now use a mirror, because you can actually focus light using a mirror. The biggest telescopes in the world do the same thing, but all you've got to do is get the shape of the mirror right, then all of the light coming from one point will be focused onto a point on your retina or onto your sensor, and you'll be able to get a picture and you can see things. Mirrors have the advantage that you can make much bigger ones which still work. If you try and make a very big lens, you get all sorts of strange aberrations and they stop working very well, which is the reason why big telescopes tend to be mirrors. But someone's been looking at this Pacific spookfish. In fact, they've just managed to capture the first one, which is they've captured alive, because it lives over 1,000 metres down. Right. When it's really down there, it's really, really dark. Spooky. And the only light which is around is really, really faint glimmerings that kind of deep fish glow in the dark. And so if you're a fish living deep down, it's really it's a big advantage to be able to collect lots and lots of light and be able to see the little glimmers of the fish trying to catch you or fish you want to catch. Yeah. And this spookfish seems to have evolved an eye using a mirror. The first one we know of in the world, which focuses much more light than you could do with a lens onto its retina, and so it must have an advantage over all the poor other fish who've only got small little lenses, and so it can see them coming much further away than they can see it. So it's obviously been quite successful.
So it gets well fed.
Hopefully, yeah. You'd have thought so.
All right then, okay. Well, have I got something for you now when it comes to saying, how things work? Because a friend of mine gave me a Prezi last night, and it's a phone charm. And I thought, a phone charm?
It just looks like a pet little thing which you tie to your phone.
It is, yes. But I've got it sort of, edged on there. But it's quite interesting because my phone's on silent. Of course, if there's any emergency, I need to be alerted. But when I do get a message of some description, then the little thingy sort of, does a strange little performance. And it's a little glass dome with a little guitar in, because she thought it would be fun. Oh, it's doing it now. Oh. You see? And so I just wonder, how does it work? Because it glows and flashes and the little guitar, rings around.
Yeah, because it's not attached to your phone at all.
No, isn't it sweet?
In fact, it started going before the phone started ringing.
So it sensed it. Yeah, it sensed it.
Okay, I think what's going on here is the way the phone receives a phone call is a base station, all the phone towers, which are all around the country, sends out a signal to say, is your phone about? Is your phone here? Then your phone sends another signal back to the base station, says, yes, I am, send me some information. And so your phone starts transmitting, and then the base station sends you the information, or if you're having a phone call, then it'll send you the information from what the person's saying at the other end, and your phone will transmit what you're saying back to the base station. Now, I think what's in this little phone charm is basically a very, very simple radio. It's sort of tuned roughly to the sort of frequency which your phone uses. And so if it detects a signal which your phone is transmitting, it doesn't have to be a very good radio because it's only 3 centimetres away. Right. And so just very, very simple, very brutal radio. If it detects your phone transmitting anything, it will think, the phone's transmitting, someone's probably trying to phone in or you're trying to phone out. I'll start the lights flashing and start the start the guitar spinning around.
It's cute. It's
very cute.
I hadn't seen one like that. And she went, I'm sure you'll find it useful. I said, I'm sure I will. But it's just great.
What I have noticed, I've playing with one of these before, is that some of them will work fine on conventional older-fashioned phones.
Right.
But they won't work on the third-generation modern shiny 3G phones. So they work on a different frequency. So the radio inside it's tuned to old-fashioned phones, but if your 3G phone is transmitting on a different frequency, like a different place on the dial on the radio, you won't be able to pick it up.
Well, this is easy. You just need a normal phone, don't you? That's the thing. Dr. Dave, thank you very much. Right, first of all then to the email. Hi, Sue and Stanley. Dr. Dave tonight then. Now, Dr. Dave, says Jackie in the Borders, leaves are now on the trees until December. With climate change, will we get to a stage where the leaves no longer fall off the trees?
Well, I don't see any... if the world does get warmer, I don't see any reason why we wouldn't. I mean, in fact, already there are some plants which can survive in our climate quite happily and keep their leaves all through the winter. I think rhododendrons don't lose their leaves in the winter, and they're fairly broad leaves. So I think... and so if anyone...
I'm puzzling at that, rhododendrons, yeah.
It's just a fact which has just jumped out of my brain. I think it's true.
Did it?
But certainly things like very narrow-leaved trees like yew trees and conifers have always kept their leaves all the way through the winter. I mean, the reason why plants lose their leaves is that basically all their leaves at once in the winter is that during the winter, if it gets very cold, even if you've got light shining on you, the rate of chemical reaction slows down so much because chemical reaction gets slower and slower the colder it gets. So if you're getting very, very cold, the rate at which chemical reactions go is so incredibly slowly. Below about 3 or 4 degrees centigrade, grass just can't grow at all. It just stops. So basically there's no point in having a leaf there when it can't grow. If it gets very, very cold and it freezes, then you get all sorts of damage to it. And basically the advantage of having a leaf there which could photosynthesize all winter isn't enough to offset the loss of losing all your leaves and having to regrow them in the spring again. So, but if you got a lot warmer, then even though there's less light during the winter, the plants would gain something by growing very slowly all winter. And they wouldn't have to dump all that energy losing all the leaves during all at once and then having to regrow them in the spring. And they get a bit of an advantage over the trees which hadn't lost their leaves. But saying that, I think there are still deciduous trees which live quite a long way south than us. So I doubt we'll lose all of our deciduous trees. Unless it gets very, very warm. And even if it did get very, very warm, when you're a long way north, it just gets so dark in the winter, there's not really enough light to bother photosynthesizing. So you might find, definitely in the north of Scotland, I'd be very surprised if you entirely lost deciduous trees. But yes, certainly there will be a tendency to increase the number of evergreen trees. Whether it will be the same species or not will depend on how they adapt. Because if you're a tree which decides to lose its leaves by the temperature, then as it gets warmer, then you'll just think, it's not cold enough, I won't lose my leaves yet. Yeah. But if you're a tree which loses its leaves by the day length, and if the day length gets shorter, then you'll just lose your leaves. Yeah. And then all the other trees which still got their leaves are going to be able to keep growing for another couple of months and grow a bit higher, taller than you. So next year you'll be behind and do less well.
Right, OK, well, getting into the light again, Andrew from Cambridge would like to know how the candles that reignite work and how they keep relighting after they have been blown out. They're great fun, those, aren't they? Dave?
They are. They always used to confuse me as a child. They're great fun. You try and blow them out and it didn't work. Evil things. OK, the way a candle works is what you've got to start off with. Basically, you've got a load of wax, which is basically, most waxes these days are petroleum wax, which is basically a relative of petrol. It's like very long petrol molecules, which all kind of stick together, and so it's solid at room temperatures. But when it heats up, it melts, and that gets sort of sucked up the wick by surface tension. Yeah. And then the wick's got a very large surface area, and it's quite warm in a flame, so the wax evaporates. Once the wax evaporates, it can then react with oxygen and burn, because it's got a very large surface area, so it can react very quickly and burn with the flame. If you blow a candle out, you get the smoke which comes off it. That's not actually smoke. That's wax, which boils off the wick and then condenses and forms little droplets of wax in the air. Now, If normally you get an ember on the end of a wick, and that's sort of glowing red, but it's not hot enough to reignite the wax. But if you add some magnesium powder into your wick, do you remember burning magnesium at school?
Briefly, yes, when we were allowed to do experiments.
Stuff which burns very, very hot, bright white flame. Scary stuff, that's the stuff. If you have, so normally when it's in the wick, oxygen can't get to it, so it can't burn, because all the oxygen is being used by the wax, which is burning around it. But if you blow it out, then oxygen can get to the magnesium, which is hot enough to keep burning. It burns very hot, which is hot enough to, it gets hotter and hotter and hotter as it slowly burns. So eventually it's hot enough to reignite the wax vapour which is around it, so the candle bursts back into flames.
All right, well, that's given an answer to that one. Thank you very much, Andrew of Cambridge, for your question. Now, talking about lights, Daniel from Meldreth wanted to know about energy efficiency light bulbs. In light of the recent news that incandescent bulbs are being phased out and people have been stockpiling them, he wants to know how cost-effective these bulbs actually are and where they are actually better for the environment given increased disposal costs.
They're certainly much more efficient. They use about a tenth of the energy of a normal, maybe a fifth to seventh of the energy of a normal light bulb for the same amount of light. Basically, because normal light bulbs give out a lot of heat, they give out a lot of invisible infrared radiation, which you can't see with your eyes, so it's entirely pointless. So basically wasting energy by producing stuff you can't see. If you look at how much energy how much the energy cost would be in a compact fluorescent light bulb over its lifetime, which is several years, it's probably going to use about £20 worth of electricity. The original light bulb, now they're really quite cheap, they're maybe about £1, so you're about £21 worth for a whole compact fluorescent light bulb's life. If you did the same thing with normal light bulbs, you'd probably get through 12 or so normal light bulbs in the same time, and it would use £100 worth of electricity. There's about 5 times as much cost in electricity as with a normal light bulb than with a compact fluorescent one, with an energy-saving one. So that's a huge advantage. Compact fluorescents do use more energy to make. They're more complicated. They need some electronics in them. But when you're buying electricity, you're buying pure energy. Whereas when you're buying a compact fluorescent light bulb, you're buying some energy because someone's had to use some electricity to make it and some stuff. Yeah. But you're also buying somebody's time to make it, lots of expensive machine time. So even though it would have cost £1, it would have used much less than £1 worth of electricity, because otherwise whoever was making it is going to be losing money hand over fist. And yes, they could be slightly more difficult to dispose of because there's a very small amount of mercury in them, but at the moment they're just going straight in the tips. They are very cost effective at the moment, I think, probably even if you include disposal costs.
All right, so stockpiling the normal ones, I don't get it, do you?
I don't really. There are a couple of things which compact fluorescents don't work very well for. One is definitely the normal ones don't work very well with dimmer switches, because the way a dimmer switch works, it sort of turns on and off the electricity very quickly. Yes. And they buzz. Yeah. And this sort of is a bit violent for the electricity being turned on and off very quickly is a bit violent for the electronics inside the compact fluorescent, and it can damage it. So they don't work very well on dimmers, and there are some light fittings which haven't really got the space for compact fluorescents, but they're getting more cunning designs of compact fluorescents which will go in more and more places these days. All
right, let's go to our next question. Steve from Cambridge wanted to know further to the question about trees. He says, why New Zealand, with a very similar climate to the UK, had virtually all non-deciduous native trees? Good question.
That is a very good question. My guess is that it would be because, although New Zealand's got a very similar climate to the UK, it's actually a lot closer to the equator. Because the north and south hemispheres are very different, mostly because Antarctica is a landmass over the South Pole, whereas the North Pole is over water. And around the South Pole there's a sort of area of sea. Basically, the South Pole gets very, very cold, and whereas the North Pole is being warmed by ocean currents all the time. So the South Pole gets incredibly cold, so you get much more sea ice, so you get more heat reflected off the white ice back into space. So basically the Southern Hemisphere is a lot colder than the Northern Hemisphere. So although New Zealand is about similar weather to us, it's a lot further north, it's a lot closer to the equator, so there's much, much stronger sunlight. So the winters have got much longer days. So in the winter, although it might snow occasionally, the plant isn't losing as much energy. In the UK, the plant's not losing much energy by losing its leaves because there's not much light there anyway. But in New Zealand, even in the winter, there's still quite strong sunlight because I haven't got the latitudes in my head. It's probably somewhere around the south of Spain sort of latitude. So very, very strong sunlight. So even in the middle of winter, it's worth the plant having a leaf there and photosynthesising and gaining more fuel.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Time to have one of a caller on air. So let's go to the phones right now. Let's welcome Tony onto the show. Hello, Tony.
Good evening, sir.
Happy New Year to you.
And a very happy New Year to you and Dr. Dave.
And you, Tony.
Thank you.
What's your question for us,
Well,
Tony?
the question tonight is, the moon was a bit nearer the Earth, I believe, the other day. When it gets nearer the Earth, does it make the tide any higher?
Yes, is a simple answer. Of course, it's always a more complicated answer. Basically, the reason why we get tides is that the moon's gravity gets weaker the further away you go from it. So because everything attracts everything else, but the further away you are from mass, the less you're attracted to it. So the side of the Earth, or the water on the side of the Earth closest to the moon, is attracted to the moon very strongly. The Earth is attracted slightly less strongly, and the water on the other side is attracted even less strongly. So you can imagine in some way the whole Earth is sort of falling towards the moon all the time, but the water closest to it is trying to fall faster, so you get a bulge closest to the moon. And then the Earth is falling a bit faster than a bit slower than that. Then the water on the far side is falling the slowest, so it gets left behind. So you sort of get a bulge with the water on one side being pulled towards the moon, and then the Earth is leaving the water on the far side behind. So you get two bulges, and the Earth spins inside the water every day, and so you get as you go round. If you're standing on the Earth, you go through the two bulges, and you get two tides. So yes, the closer the moon is, the bigger the difference is going to be between the gravity on the close side and the far side. So the bigger the tides will be.
It's sort of a mini tsunami, do they call it, whatever it is?
Tsunami. I mean, it is
like
actually a tidal wave. I mean, in fact, the real tidal wave, there are sort of two real tidal waves going around the Earth all the time as the Earth spins inside the moon's gravity. Of course, whether you get the highest tides at the time when the moon is closest isn't necessarily the case, because you've also got the sun.
Yeah.
And so basically you get the biggest tides when the moon is either in between us and the sun, or exactly on the opposite side. Because that way, if the moon's between us and the sun, then both the sun and the moon are pulling in the same direction. So you get much bigger. It pulls very hard on the water closest to them, and much less strongly on the water on the other side. So you get a spring tide. If they're at right angles to each other, they're sort of pulling in opposite directions, so you get a much weaker tide, so you get a neap tide. And also when they're opposite each other, because the water closest to the moon is getting pulled very strongly towards it in one way, but weakly in the other direction by the sun, and the water close, basically because the moon's on the other side, but it all works out. Sorry, I need to draw a diagram.
Arms
are going everywhere in here, Tony.
I get the general...
You get the general gist. Thank you. You get the really, really biggest tides of the year, or even over several years, when the moon is at its closest and the moon and the sun are lining up.
Yep.
That's when you get the really, really big tides.
Yeah, lovely. I've learned a lot tonight, Doctor.
Thank you very much, Tony. Thank you.
Thank you, dear. See you soon.
OK, bye-bye.
Bye.
Now, Luke has sent an email in. How do materials change colour with temperature?
So I think he's thinking of those, like things like the global hypercolour T-shirts and the mugs where you pour hot water in and they
That sounds about right, yeah.
They change colour and you get patterns which appear and disappear on the mug as you pour water into them.
Yeah.
And Chris desperately wants one of these for the Naked Scientist, so you have a mug which where his lab coat disappears as you pour the water in, but we won't go into that.
Right, okay.
But anyway, the way a lot of these work is that inside them, in the dye, which is the colouring, you've got two materials. One of them is a dye which changes colour depending on the acidity, a bit like litmus paper. So if you remember with litmus paper, if you put it in acid, it goes red. If you put it in alkali, it goes blue. Red cabbage does the same thing. So if you put vinegar on red cabbage, it goes a nice red colour. But if you try and boil red cabbage in Cambridge water, which is quite alkali, it'll go a blue colour.
Oh, right, okay. Kitchen science coming in there.
Kitchen science, indeed. Now, what they do with this dye in the mugs and things is they then add an acid which will only melt at a certain temperature. And acids don't really act as acids when they're a solid. So when they're a solid, you've got a bit of alkali lying around, so the material is one colour.
Yeah.
But then when you heat it up, the acid melts, starts acting as acid, changes the colour of the dye. The dye suddenly is in an acidic environment. It's an indicator it changes colour. So the mug changes colour. And then as it cools down again, the acid crystallises out again, stops acting as acid, and it goes back to its original colour.
Hello to Paul, who's a new listener from Colchester. Lovely to have you listen to the show, Paul. Paul asks you, Dr. Dave, what causes static electricity?
Okay. Basically, static electricity is a build-up of charge. So inside all the atoms of the universe, basically, in the centre of them you've got a lump of positive charge, and around the outside you've got a whole cloud of little electrons. Mm-hmm. Positive attracts negative, so normally they're about neutral. You've got the same number of electrons as protons, so it's neutral. And the electromagnetic force is incredibly strong, so it's very hard to get a very big difference in the number of electrons and protons. So you've got basically everything's neutral. However, some materials will attract electrons slightly more than others. So, for example, rubber attracts electrons slightly more than hair or wool does. Right. So if you touch rubber onto a hair, some electrons tend to move from the hair onto the rubber, just a few of them.
Right.
And then take it away again, they'll stay there. So the balloon will become slightly negatively charged, and your hair will be slightly positively charged.
All right, a bit like a curry comb on a horse. Yes,
yeah.
A rubber curry comb on a horse.
Yeah,
right.
Yeah,
okay,
so
yeah.
And then if you rub this balloon on the hair, every time it touches a hair, some more charge will move onto the balloon, and every time it releases, it will stay there.
Right.
So slowly you get a load of negative charge on the balloon, and the hair is positively charged. So now they'll attract each other because positive attracts negative. Uh-huh. So if you move the balloon near your hair, it'll suddenly get attracted to the balloon. You get that really weird feeling when you move the balloon near your hair. If you ever done
I know you do, Dave, because you're always doing stuff like that, and you're quite hairy.
I do that. For some reason, balloons charge by the best on my legs.
Do they?
Yes.
Right. Good for that.
So mostly static electricity is due to things rubbing against each other. So if you have rubber shoes and you walk across a wool carpet, then you'll slowly move charge onto your shoes, and you'll slowly become negatively charged. And then if you touch something which is attached to earth, like something metal.
Well, yes.
You're going to get sparks jumping.
I get this all the time because, as you can see, our rubbish bin there is a metal bin with a rubber sack in it.
Yeah.
And often I go across to put something in the bin and go, ugh! I just get charged from it.
Yeah, it's probably not the bin which is you're getting a charge from. It's probably more your shoes rubbing across the carpet.
Right.
As you walk across the carpet, you charge up.
Right.
And then when you touch the bin, because the bin's a good conductor, and you're probably very negatively charged or positively charged, depends what your shoes are made, your soles of your shoes are made out of.
Right.
You've got a load of charge. When you move your finger near the bin, all the charge will run to the end of your finger. And when you get close enough, it will jump from your finger to the bin through the air, forming a little spark.
Yeah. Will says that he often gets it on the top of his car door. Why is that?
Basically, air rubbing across things can also charge them up. So in the same way, if a material your car's made out of likes electrons more than air does, then electrons will get transferred from the air as it flows past to the car paint or whatever. Yeah. So the car charges up. It's now but less of a problem, but you used to have tyres which were made out of rubber, which are very good insulators, so the charge would build up very strongly on the car. You get out, you touch something, a big shock. It's a really big problem with helicopters because they don't touch the ground.
Oh right, yeah, of course.
So there's nowhere for this charge to escape to. So if, especially on a dry day, if there's a helicopter, you've especially got a big whirling blade at the top, which is moving through lots and lots of air, lots of rubbing against the air. You can build up really big charges, thousands and thousands and thousands of volts. And then if you're a guy who's coming down a winch rope, and then you try and get on a ship which is earthed, suddenly all of that charge is going to try and run through you, and it can be very unpleasant and quite dangerous. So if someone is being dropped out, lowered down a winch rope, what they tend to do is, if you're standing on a ship, you get a kind of hook which is earthed, and you touch that to the winch rope first.
Right.
So all the charge runs down through your hook and through a wire onto the ship. So it doesn't run through the guy who's coming down the winch rope, and he doesn't get electrocuted, basically.
Well, I didn't know that. We've got one here from Sean. He says, if I were to light a match from a matchbox in space, although there would be no flame because there is no oxygen to start a fire, would the flint of the match still ignite? So that would be like a lighter, if you think about a lighter or something like that.
I think it depends. The flint on a lighter, I don't think would ignite, because the way that works is you have a very brittle metal which will react very strongly with air. Something like osmium, I think, is involved in it sometimes. And you get little lumps of that which get knocked off. When they get knocked off the metal, you put quite a lot of energy into them, they get hot, and they get hot enough to start burning in the air. So the flint is actually little bits of metal burning in the oxygen of the air. However, a match, I think, is different. You can get matches which will actually strike underwater, and quite often those have got an oxidizer inside the head. It's basically a small piece of explosive, and so I think the match head would ignite, but not the rest of it wouldn't burn. You wouldn't get a flame. So I think a match probably would get a flare off the head, but not the body, and with especially red matches. But the flint off the lighter wouldn't. You just get little bits of metal flying around.
Now, Jules in Lound says, is it possible to drink rainwater without boiling it? Would you?
Rainwater, yes, definitely.
Okay.
Rainwater has basically water's evaporated.
Yep.
When water evaporates, no solids can go with it, because if it's a solid, it's not going to evaporate and turn into a gas. So you basically just got water, and so no microbes or no disease-forming things could get out, couldn't evaporate as well. So the water, you get lots of water vapour going up as a gas, then it condenses in clouds and falls out of the sky. So rainwater, this is the same process of distillation, it forms very pure water. The only things which could possibly contaminate it are things which could also be gases, things like carbon dioxide. So unless anyone is spraying an awful lot of poisonous gases into the air where you are, which I doubt, rainwater is perfectly safe to drink. Once it hits something, of course, then it can pick up whatever's landed on what it's hit.
Yeah.
So, I mean, drinking rainwater out of a drain might not drain off your roof, or gutter is not necessarily a good idea, depending on the state of your gutters. But yes, straight out of the sky, rainwater is perfectly safe.
Kathy from Colchester wanted to know, why is it that at night she can see lights in the skies of aeroplanes that don't appear to be moving, whereas during the day you can see the plane moving?
I would have thought it's to do with the fact that you can probably see a plane much further away at night than during the day. Probably two things. One is that you can see a plane further away because you've got a really bright light on it, and so you can probably see it 10, 20, 30 miles away, just from the light. Whereas during the day, by the time it got that far away, you'd be so small you'd hardly see it.
Yeah.
So basically you're seeing planes further away, so they're going to be moving across the sky more slowly because they're further away, basically. The other thing is that when at night you've got less points of reference. So unless you've got a very bright starry night, you're somewhere out in the countryside where you can see the stars nicely. If you look up at the sky, it looks fairly black. There's not a lot of things to compare the movement of the planes against. Whereas during the day, you've got bits of cloud and things. So you can see the plane moving past things, so you know it's moving, whereas it's very hard to judge a very, very small change in angle if you've got nothing to judge it against. But I think the biggest effect is probably you can see them from further away.
One last one from Jeff, this one, who says, does the sun rotate just like the Earth does? Well, I've never thought about that one before, so good question, Jeff.
It is a good question. The sun does rotate, although not quite like the Earth does. The sun rotates in quite an interesting way, in that it doesn't all rotate at the same speed. I think the equator of the sun rotates about once every 25 days. Whereas if you get up to sort of 34, about similar latitude to us, it's rotating once every 27 days.
Right.
So if you imagine it, the middle's going around more slowly than the top.
Yeah.
Because the sun isn't a solid lump like the Earth. It's made out of very hot gases. If you tried to stand on it, you'd sink very quickly. It's much less dense than it's less dense than water.
Yeah.
So it's much less dense than water, and so it's all flowing around. Because hot gas expands and rises, and the centre of the sun is hot, you get what we call convection current. So in some areas of the sun, you'll get hot gases rising upwards, and other places you'll get them falling. Because the centre of the sun is smaller, it's going to the speed. If you imagine a roundabout. If you're near the middle of the roundabout, you're not going to be turning as fast as if you're out at the edge. You're not moving as fast because for every rotation on a roundabout, you're going to be going less far when you're near the middle than when you're on the outside. So the gas which is moving up from the centre of the sun isn't moving very far, isn't rotating very fast because it was nearer the centre. So places where the gas is rising upwards tend to rotate more slowly than places where it's falling down again. So different parts of so you get huge winds forming around the sun. So some parts of the sun are rotating at different speeds than others.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.